Hello and welcome to a GeoDict tutorial. My name is Janine Hilden, I'm an application engineer at Math2Market, and in the following video I will show you the cool new structures in GridGeo that are shipped with GeoDict 2022. They are particularly interesting if you use additive manufacturing as, for example, laser sintering in your production workflows. The first group of new grid structures are the Strut-based lattices. And afterwards I will show you the triply periodic minimal surfaces. We will work on the surface of a triply periodic minimal surface and will run a flow simulation on it. First of all, I will shortly show you the usual GridGeo options. You find them up here in the menu bar when we select Model and then click on GridGeo. Now the GridGeo section opens down here. For example, select the grid of spheres from the pull-down menu and just click Generate. That simply produces a regular sphere pack, as you can see here. You can also create perforated foils. Just click Generate again. And of course you can also define a custom grid here with user-defined grid. Additionally, there are several predefined structures. Many GeoDict modules have such helpful predefined GeoPy scripts, which use the corresponding modules either with a simplified user interface for special cases or specific post-processing. You can also find them if you select Geo App from the menu bar and select the corresponding module, here of course GridGeo. Now a second pull-down menu contains all the predefined structures for GridGeo. The first two are the new ones that I will show you in this video. We start with 1 Strut-based lattices, and for the moment just click Run. As always in GeoDict, the default parameters deliver a nice structure showing you the functionality of the respective module. As you can see, a lattice-like structure is generated. The lattice is constructed from these struts here, which connect in nodes. There are many different possibilities for the strut placement. They can be oriented in different directions or crossed differently. Let's just open the Options dialog by clicking Edit, and I will explain some of the parameters to you. So here we have the lattice type. We generated the all-face centered cubic lattice, which has a cross point in the middle on all cell faces, as we can see in our structure in the viewport. For example, we could also choose body-centered cubic lattice, click OK, and run. And now you can see that the struts now meet at the cell centers. You can find images of the other lattice types in the user guide, which opens if you click Help here. Or you can find an overview on our website. The link is in the video description. Again, click Edit. And a lattice consists of periodic cells, and you can determine the length of these cells here. Then you can define the diameter of the struts. Therefore, we have two parameters. The first one controls the strut diameter near to the nodes, and the second one defines the diameter in the center of the struts between two nodes. Let's just change the center of strut diameter to 0.5 millimeters, and then the struts will be thicker in the middle. With the last parameter in the upper panel, you can control the number of voxels in one periodicity cell. This defines the resulting voxel length and thus the resolution of the lattice. We don't change this parameter and just click OK and run. Now we see that our lattice changed. The struts are now thicker in the middle than near the nodes. Again, open the parameters dialog. The last thing we can control is how many copies of the periodicity cells we want to generate. For example, we can create more periodicity cells in X and Y direction. I simply enter 3, and then just one cell in Z direction. Then we obtain a flat lattice. Click OK and run. This way, change the parameters as desired and create your custom strut-based lattice. This was the first new GridGeo predefined in GeoDict 2022. Now let me show you the second one, the triply periodic minimal surfaces. I will call them TPMS from now on. So first, just click Run again, so we can see what it does. In the description here on the left, you find a paper with detailed theory on TPMS. You can also find the link in the video description. Shortly summarized, they are mathematically curated surfaces which are not self-intersecting or enfolded. They are called triply periodic as they can be packed together in a periodic 3D pattern. The second part of the name, minimal surface, refers to locally minimizing the surface area for a given boundary, resulting in a mean curvature of 0. Basically, all selectable TPMS types here are produced by different sine-cosine functions, as one could also guess from the sine-like waves we can see everywhere on our structure. Just click Edit and examine the parameters for this grid. We now created the gyroid lattice here. For the different lattice types, we can also define the shape mode. By default, it is set to cylindrical, as this is an often used shape, for example, in heat exchangers. But a square shape is also quite common in other applications. Just set it to square for now. Then we can define the number of repetitions in the 3 directions, and down here we define the domain size and the voxel length. But due to the underlying mathematical functions, we cannot define the thickness directly. Instead, we have the threshold method here. For the moment, just click OK and run. So now we have a square-shaped gyroid, and what we can also see here is that the volume field tab is available. Just enable the checkbox and disable the structure, and now we can see the volume field the structure is based on. With the underlying functions, this volume field is produced, and with the threshold values, this field is segmented to a structure. We can also preview the results of different thresholds. If we move the volume field tab, and move the slider, or enter different values directly. The default value for our current lattice was 0.6, and if we enter this value here, we can now basically see our current structure just with more colors. If we set the mode to smaller equal, we invert our structure. So click Edit again and change the threshold mode to smaller equal, click OK and run. Disable the volume field again and enable the structure, and we can see that it is inverted compared to before. Additionally, we can define a threshold range for the segmentation. So here select smaller greater, and now we can set a lower and an upper threshold. We just generate the structure again. And now we have walls in our lattice, where the wall thickness is controlled by the given threshold range. So this way you can set the threshold as needed. And now let's also change the domain size a little bit. While the number of repetitions does not control the domain size, it is instead controlled by the length values down here. If we enlarge our structure in one direction without changing the number of repetitions, the sine-like curves in this direction will just be stretched, or if we use a smaller value for the length, it would be compressed. I just want to have a cubic lattice, so I change the length in Z direction to 3.5 mm and adjust the number of repetitions by entering 4 for the Z direction. And click OK and run again. Now I have a cubic lattice with 4 waves in each direction. There are again more types for this lattice, and they are also shown in the GridGeo user guide and on our website. So if you are interested in this kind of structure, please have a look in one of them and see if there's also a right lattice type available for you. We now will generate one other type, for example the Schwarz Diamond. Let's set the shape back to cylindrical and reset the threshold mode to greater equal. OK, and run. And as you can see, this one looks also very cool already. But often the lattices are manufactured with laser sintering, where a powdered material is melted with a laser. So the structures are usually not as perfectly smooth as it looks here, where I have selected smooth rendering in the structure tab. Instead, they have a rough surface. Therefore, we will use the Roughen Surface option in GridGeo. So select Model and then GridGeo. In the GridGeo section, we select Roughen Surface and click Edit. Here, we use the stochastic roughness to add and subtract small features to and from the surface to gain a powder-like surface. Now, either change the unit to voxel or just look in the project status here on the left to find out the voxel length. Then we know what feature radius could be reasonable. So we have here a voxel length of 10 micrometer, so a feature radius of 3 would be much too small. Just set it to 40, for example. Then we can also control how much the features should stick out. We set the maximal distance to 30 microns. And then we could check Keep SVP if we do not want to change the solid volume percentage of our structure as it is, but we won't do that now. So just click OK and generate. And as you can see, we have now a realistic laser-sintered lattice model. Finally, we just run a fast flow simulation on our lattice to get a nice flow visualization. Therefore, select Predict and then FlowDict. Select the Stokes-Brinkmann equation and click Edit. As GeoDict needs some material properties to run a simulation, here in the Constituent Materials tab, click on Undefined for ID 0 and the material selector opens. Unfold Fluid and select Water. Click OK and click on the second material. Here unfold Solid and select Aluminum. Close the dialog again by clicking OK and run the simulation. This will take about 1 to 2 minutes. Then, as with all simulations in GeoDict, the results are shown in the Result Viewer. In the Report tab, we find the permeability tensor with the permeability in Z direction and some additional results down here. We want to visualize the result in 3D, so move to the Flow Visualization tab and click Load. Here just click OK and we see the flow field in the visualization area showing us in red where the flow is faster and in blue where no flow happens at all. Select the Structure tab and just clip the structure to see more of the flow field. For my camera angle, the Y side is in the front, so I move the Y slider from the right to the center approximately. Then move to the Volume Field tab and click Edit Color Map. Set the data range to manual and for high threshold, enter 2.4 E-5. Now the legend shows the entered maximum value in the top. Enable transparency and move the left point down by just clicking on it and dragging it. Move the right point up and now the fast flow regions can be seen very well, while the slow flow regions are nearly invisible. Also, the structure shines through the transparent flow field, leading to a beautiful visualization. If you do not like the colors, you can also change them here in the Color preset. For example, select Cold and the flow field is visualized in blue scale colors. Open the visualization sidebar here on the right, unfold Legends Overlays, unfold Volume Field Legends, and here you can change the decimals. For example, set the decimals to 0. Now the legend looks much better. Deselect Bounding Box so we cannot see the boundary lines anymore. Now we have a nice flow visualization for our flow simulation results. This is the end of this video tutorial. I showed you the new predefined grid structures in GeoDict 2022 and how to roughen the surface of a structure and run a flow simulation. Finally, we visualized the flow field with transparency. If you found this tutorial helpful, please check out our Math2Market channel for more GeoDict videos. Goodbye!